Hello and welcome to another science video. Today I wanted to discuss the topic chemical bonding and structure. The topics this video will cover include the octet rule, Lewis structures, and resonance structures. Firstly, you should know that covalent substances are formed by covalent bonds between nonmetal atoms. Each bond is strong and consists of a shared pair of electrons. Here's a diagram showing how strong covalent bonds are in comparison to other bonds. Now, let's start with the octet rule. The octet rule states that the most stable arrangement for an atom to have is 8 electrons in its outermost energy level, along with the electron configuration of a noble gas. Noble gases are the elements that make up group 18 in the periodic table. An important feature of noble gases is that they have a full valence shell, with 8 electrons in its valence shell. We're expected to use the octet rule to construct Lewis structures that represent the bonding between atoms in a molecular covalent substance. When forming a molecule, an atom will tend to make as many covalent bonds as possible. Let's take carbon tetrafluoride as an example, or CF4. The maximum number of covalent bonds is 4 because there are only 4 valence electrons in carbon atoms. Lewis structures are electron dot diagrams that represent the bonding in a molecule. They show that the bonding electrons and lone pairs of non-bonding electrons. In these structures, pairs of electrons can be represented by a line, crosses, dots, or a mixture of dots and crosses. Here are the steps involved to construct a Lewis diagram. We will be constructing the Lewis structure for PCl3, or phosphorus trichloride. Step 1. Find the total number of valence electrons in all of the atoms in the molecule or ion. Remember, electrons should be added for negative ions and subtracted for positive ions. The number of electrons added or subtracted should be equal to the charge on the ion. So let's write the total number of valence electrons for PCl3. Phosphorus has 5 valence electrons and chlorine has 7. That would be 5 plus 3 times 7, which equals 26. Note that in this compound is not an ion and therefore does not have a charge. Step 2. Determine the electrons that each atom needs to complete its outer shell. According to the octet rule, the majority of atoms require 8 electrons to complete its valence shell, except for hydrogen, which requires 2 electrons. Back to our example. Phosphorus requires 3 electrons and each chlorine atom needs 1 electron. Ergo, there are 6 bond pair electrons. Step 3. To get the total number of bonding electrons in the molecular ion, subtract the number of bond pair electrons from the total number of valence electrons. In this case, that would be 20. Step 4. Now let's draw the skeletal structure of the molecule with the least electronegative atom at the center, and connect all the atoms using only single bonds. Pause. Note that there are some molecules where the central atom does not have the lowest electronegativity value, for example, H2O and NH3. To find the least electronegative atom, we can use our knowledge of the periodic table trends. Electronegativity decreases down a group and increases across a period. Therefore, we know that phosphorus would be more electronegative than chlorine. Step 5. Lastly, we need to complete the outer shells of the atoms in a molecule or ion, including all non-bonding or lone pairs of electrons. If the outer shells of all atoms cannot be filled, then it may be necessary to use multiple bonds between atoms. As we're drawing this diagram, we can identify that the shells of all atoms are filled, fulfilling the octet rule. Well, now that we know how to draw Lewis structures, we can explore resonance structures. When molecules contain multiple bonds, double or triple bonds, there is more than one possible Lewis structure that can be drawn. These structures that can be drawn in different ways are known as resonance structures. Resonance structures exist for all molecules where there is more than one position for a multiple bond in a molecule or polyatomic ion. The number of possible resonance structures is equal to the number of different positions for the multiple bond. Let's have a look at the example of a carbonate ion. None of these structures represent the actual structure of the carbonate ion. The actual structure is a resonance hybrid structure. In the resonance hybrid structure of the carbonate ion, all the carbon-oxygen bonds are identical and are intermediate in strength and length between a single and double bond. Let's now move on to delocalized electrons, because now that we know that electrons in a covalent bonds are located in a specific position within a molecule, this is an important idea as it helps us understand that covalent molecules have a defined shape determined by the orientation of these fixed or localized bonds in space. However, in some molecules, the bonding electrons, specifically those involved in a multiple bond, are less restricted than this. Electrons that are shared between more than 2 nuclei in a molecule and are not confined to one location are described as delocalized. Delocalized electrons give greater stability to a molecule or polyatomic ion. They exist in any molecule for which there is more than one possible Lewis structure and therefore more than one possible position for a multiple bond. If we look at the Lewis structure of ozone, O3, we can identify that a different Lewis structure would be equally valid. We can explain this validity by considering the electrons from the double bond have delocalized and spread themselves equally between both possible bonding positions. The true structure of an ozone molecule is a hybrid of the Lewis structures. This is where the concept of resonance structures have a role. And that is a brief overview of Lewis structures. For more resources and information on this topic, visit our website linked in the description below, and attempt the worksheet attached to challenge yourself and self-assess using the detailed worksheet attached. Make sure to subscribe to BMAT EDU and happy revising!